Alright, suppose we have a vector subspace M, which is a subset of n-dimensional vector space, and spanned by an orthonormal basis consisting of vectors E1, E2, up to ED. And let's define a map P from Rn to M, defined as this. And such a map is called an orthogonal projection. And in this video, we will study various properties of such orthogonal projections. Okay, let's start. First of all, let us consider the meaning of this projection operator. First, let's consider this inner product. So, according to what we have learned before, this is equal to the norm of x times the norm of EJ times and cosine theta, where theta is the angle between the two vectors. I mean, actually, this was the definition of theta, but now we can interpret as the angle between these two vectors. So theta, EJ here, and x here. Okay. But EJ is a normalized vector, so its norm is 1. So this one is equal to 1. So this is just x norm times cosine theta. Now let's multiply this with EJ vector. EJ and EJ. So this one, the magnitude is this. So this is the magnitude of this vector is this x times EJ. So that is the length of this x vector is x, and cosine x, if we multiply by cosine x, that will be, if we draw this right-angled triangle, this length is this inner product. Now we multiply by this vector, so it is a vector in this direction, in this direction, with length of this, okay? Because again, this, the length of this EJ is 1, so the length of this vector should be equal to the absolute value of this. Okay, so in this sense, this is a projection of vector x on this axis spanned by EJ. Okay, so this is so x is projected onto this vector EJ. Okay, so that's the meaning of this term. Now we do this for each EJ that spans this subspace, and then add them. So that is the projection. Okay, next, let's show that this projection is a linear operation. Okay, suppose we have x and y, that is that are vectors in our dimensional space, and alpha and beta are real numbers. Okay, then by saying a linear operation, we mean this: p of alpha times x plus beta times y is equals to alpha times px plus beta times py. Okay, so this means linear operation. So let's show this. This is equal to, according to the definition, we have j from 1 to d, and the inner product, alpha x plus beta y times ej times ej. Okay, but this inner product was a linear operation. Actually, it's a bilinear operation, but so we can split this addition and multiplication by real numbers as this. So alpha and x times ej plus beta y ej and ej. And we distribute this again, then we can put alpha out, and j from d x ej times ej plus beta j from 1 to d y ej ej. But this one, this part is just p of x, px plus, and this one is py. So it's a linear operation. And the next property, so second property, is this: px times y is equals to x times py. So the place of p can be here or here, it doesn't matter. So this is again easy to see. Just apply the definition. Left hand side becomes, just apply the definition, and we have x times ej times ej and y. And by using the linearity of the inner product, we have, so we can take this summation out and this inner product out, and what's left is ej times y here. And of course this is commutative, so we have ej times y ej. And now let's put this constant into here. Okay, so we have ej x and y ej times ej. And now j appears only in this part, so we can put j inside. So let's put x and the summation over j y ej ej. Now we have x times py, and that's it. Okay, now next property. If x is already a member of the subspace M, then its projection on M is x itself. So suppose x is in the subspace M. Then this implies there exists a1, a2, and so on up to ad, which are real numbers such that x is a linear combination of the basis vectors. So j from 1 to d, a, j, e, j. Right. Now let's apply the projection. So according to the definition, this is x times ej, ej. Now substitute this. We have j from 1 to d. Let's use a different index, not j but I, let's say. I from 1 to d, ai, ei. And times ej, ej. Okay, so let's take this out, and from j from 1 to d, and I from 1 to d, ai, and ei, ej, ej. Now, since we have an orthonormal basis, this is equal to Kronecker's delta. So that means, so j, let's just abbreviate, j and ai, and delta ij, ej, right? So Kronecker's delta is equal to 1 if I is equal to j, otherwise it's 0. So we run I and j both from 1 to d, but only when I is equal to j, the term remains. So what we get is this. from j from 1 to d, we have aj times ej. So that's it. So, but that is actually equal to x, right? Okay, so that's it. And the fourth property is that for any x, if we apply the projection twice, then it is same as applying the projection only once. And this is very easy to see because for any x in the n-dimensional space, p of x is in M, by the definition. But from the previous result, since p of x is already in M, then applying again the projection doesn't change that vector by part 3. Okay, and we're done. Okay, next, suppose a vector subspace is given. So M is given. Then we define for this M another subspace called M perpendicular or orthogonal as this. So it's a set of vectors, n-dimensional vectors, such that for any vector x in M, the inner product between y and x is equal to 0. So what this means is that M orthogonal is the set of all vectors that are orthogonal to any vectors in M. By the way, in case you forgot, the inner product being equal to 0 means these two vectors are orthogonal to each other, because in that case, assuming they are non-zero vectors, the angle between these two vectors should be pi half, because cosine theta should be equal to 0. So from this definition, we can, for example, show the following. Suppose x is a vector in M and y and z are vectors in M orthogonal, and alpha and beta are real numbers. Then the inner product between x and any linear combination of y and z. So if we calculate this and using the linearity of the inner product, we have alpha x y plus beta x z. But since y and z are in M orthogonal, so this should be equal to 0, and this should be equal to 0. So the result is 0. So that means the linear combination of any two vectors in M orthogonal is again orthogonal to M or X. So that means M orthogonal indeed includes all vectors that are orthogonal to any vectors in M. What about the common elements between M and M orthogonal? Let's see. So suppose x is in the intersection between M and M orthogonal. Then, by the definition of M and M orthogonal, so since x is in M and also in M orthogonal, the inner product between x and x itself should be equal to 0. This is because, so the first x belongs to this and the second x belongs to this, but these x's are of course the same x. So anyway, so this should be equal to 0. So that means the norm of x should be 0, and that means x should be the 0 vector. So that means the only common element between M and M orthogonal is the 0 vector. So based on these properties, we call this M orthogonal as orthogonal complement of M. Okay, now let z be any vector in M and x be any vector in the n-dimensional vector space. And consider this inner product between z and x minus px. Okay, so let's expand this, and we have z times x minus z times px. But using the property of the projection operator, we can move this p to here. So z times x minus pz times x. But z is already in M, so applying p doesn't change z. So that is zx minus, so pz becomes just z. X. So this one is the same as this one, so the result is just 0. So what this implies is that x minus px belongs to the orthogonal complement of M. In particular, when z is equal to px, of course this is in M, then the inner product between px and x minus px, this should be equal to 0. And you can directly check this by expanding this left-hand side. So that will be px times x minus px times px. So we can move this p to here. So that is px minus ppx and x. But if we apply the projection twice, that is same as applying only once. So that is this minus px and x. So px times x, minus px times x, so that should be equal to 0. So based on this observation, let us decompose x into two parts. That is px and x minus px. As trivial as it seems, this has an interesting consequence. That is the Pythagorean theorem. So let's write it down. So x norm squared is equal to px norm squared plus x minus px norm squared. So what this implies is this. So if we have a vector x, then we can project this onto the subspace M. So this is subspace M. So that will be px. And x minus px would be something like this, some vector like this. So this will be x minus px. And they are orthogonal to each other, right? So of course this vector is same as this vector. So we have the Pythagorean theorem for this. So px, the norm of px squared plus the norm of x minus px squared is equal to this norm of x squared. So that's the Pythagorean theorem, exactly. And we can also show that this orthogonal decomposition is unique once the subspace M is given. Okay, to show that, suppose we have two decompositions, let's say x1 plus x2, and also x1 prime plus x2 prime. Okay, and x1 and x1 prime are in M, and x2 and x2 prime are in M orthogonal. Okay, these are the assumptions. So from this equality, we have x1 minus x1 prime equals to x2 prime minus x2. But this one, x1 and x1 prime, they are both in M, and x2 and x2 prime, they are both in M orthogonal. So that means, and these two are equal. That means these are in the intersection between M and m orthogonal. So that means they must be equal to the 0 vector. Therefore, this is equal to 0 vector. From this, we conclude that x1 is equal to x1 prime and x2 is equal to x2 prime. And we're done. So the orthogonal decomposition of a vector is unique. So because of this uniqueness of orthogonal decomposition, the effect of projection operation is unique. Okay, it doesn't depend on the choice of the orthonormal basis. Okay, so whatever the orthonormal basis set is, we can always have the same projection onto that vector subspace. Okay, so that's it for this video. See you later. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.